Howdy folks, and welcome to the channel. Today we're going to be talking about plugins. I've been meaning to make a video on how to create plugins for SeismicFlow for a while, and quite frankly, this is pretty much the most important functionality of SeismicFlow, because to the best of my knowledge, I don't know a lot of commercial or industrial applications that allow you to write plugins and directly interact with the GUI. Make no mistakes about this mechanism, guys. This is very different from what you've seen from some applications that actually allow you to write plugins. This is completely different. This gives you complete power of Python plus complete control over the GUI of the application. So practically you have as much power over the application as I have as the developer. So there's nothing I can do that you guys can't. So this is the beginner's guide on how to create plugins for SeismicFlow. In this episode, we'll be covering a couple of examples on how to interact with the GUI of the application, along with how to create custom algorithms. So here's the first example I have ready for you guys. These examples are ordered from basic to advanced, and they show you how to use the inner functionalities of SeismicFlow. The first script I have for you is the derivative.py. From the top of this script, you can see I'm importing numpy as np. Then on the third line, I'm writing a condition if self.tensor_data is not none. The first question that comes to mind is, what is self.tensor_data? Self.tensor_data is your active data, the data that is currently selected on the data tree. So on the data tree, there's an active data that you've loaded, seismic data. That's called self.tensor_data. Now, the names that I've chosen for class attributes and methods are a little arbitrary. I totally get it. I came up with them on the fly and I really didn't give them much thought. So don't come after me for the names, but if you guys have any recommendations, I'm totally open to considering them. Then we go, if self.tensor_data is not none, we're checking if there is an active data. Practically, we're checking if you have loaded anything into the application. Since we have two major different kinds of data here in the application, we either have NumPy tensors or we have pandas data frames for well logging information. So self.tensor_data could be either. You could also check to see if self.tensor_data is an instance of pandas data frame or a NumPy tensor. This would be an extra check on the data you're working with. On the next line, I've written self.tensor_data equals np.gradient. As you guys might know, I'm calculating the seismic attribute first derivative as an example for you guys to see how we could create custom algorithms for SeismicFlow. When you're writing an algorithm that uses self.tensor_data to create a new data, you need to assign the calculated data to the active data and then add it to the data tree. So here we're doing the reassigning. So we're calculating something out of self.tensor_data, the active data at that moment. We're calculating something out of it and we're assigning it to the active data. This is going to be our new active data. And then we're going to be adding it to the data tree. Here, as you can see, we have self.metadata. As the name implies, self.metadata is a dictionary that holds information for all the data sets you load into the application. Now, the key to that dictionary is called self.filename, as you can see here, which is the name of the active data. What we are doing on this line is essentially defining a new data, which is going to be called first derivative. Since first derivative is calculated from the main seismic data that we had, this is going to be added as the child of the active data we had. So the logical thing is to have the name of the parent, the seismic data, and also the name of the attribute first derivative as the whole key. So this part of the name is going to be used for the name of the child in the data tree. So here on this line, what we essentially did was to reassign the metadata of the parent for the child, because everything is the same except the template. So we have to overwrite the template. Since the image is no longer the original seismic image, it's the first derivative of the seismic image, we change the template to first derivative. So that's the only change the metadata has to go through. After we're done setting the metadata for our new data, we call the addTensor method and pass both the name of the new data and self.tensor_data, which now contains the first derivative we calculated from the original data. The addTensor function is used to add data to the data tree. Now let's talk about how I'm calculating the first derivative. I'm using the NP gradient method to calculate the first derivative of the seismic image. The first derivative seismic attribute requires us to compute the derivative along the time axis. A convention in SeismicFlow is that seismic datasets loaded into the application are stored as four-dimensional NumPy tensors with the shape, time, inline, crossline channel. These 4D tensors always include a channel dimension. So when you load seismic images, even if they're 2D or 3D, they are always represented as four-dimensional NumPy tensors. Keep in mind, time is always the first dimension. So since time is the first dimension, I'm calculating the derivative along axis 0, which corresponds to time. The reason we're using NP gradient is that it produces an output image with the same shape as the original seismic image, so the size of the image remains unchanged. So this is the most straightforward way to run functions in SeismicFlow. We're executing everything in line on the main thread. You could call it the beginner approach. But we also have more advanced ways of running functions. The real question is, why do we even have multiple ways to run them in the first place? The thing about SeismicFlow and any GUI application is that the main thread is responsible for both keeping the interface responsive and running your code. Now, if you run something computationally heavy in line, meaning directly in the main thread, the application will freeze. That's because the main thread cannot do two things at once. It has to choose between updating the GUI or running your function. So if your code performs a long mathematical operation and you run it in line, the interface becomes completely unresponsive until that function finishes. In 2025, that's just not acceptable. It's bad design. You can't have a GUI that locks up just because it's calculating something. The proper approach is to offload that work from the main thread so the GUI remains responsive while the computation runs in the background. So how do we actually do that? One solution is to use threading. Threading allows you to run a function on a separate thread, keeping the main thread free to handle the interface. This way, your application stays responsive even while a background thread handles a long mathematical operation. If you're just testing something quickly, sure, you can write a basic script that runs everything in line. That's fine for experimentation or debugging. But if you're building a plugin you plan to publish or share with others, this approach is not acceptable. Inline computation blocks the main thread, and even lightweight operations can freeze the interface. In production, that's just not okay. So here's the general rule. Anything GUI related should run on the main thread. Any computational logic or processing should be moved to a separate thread. Setting up multiprocessing manually can involve a lot of boilerplate and synchronization logic, but in SeismicFlow you don't have to deal with any of that. I've already built threading support into the platform. You can use the built-in tools to run your functions off the main thread easily, and it's actually simpler than the basic example we started with. Now let's move on to the second example we have here. I called it the derivative thread runner. Let's see the difference. Here, we defined a function, def compute seismic derivative, and it takes one argument, tensor data. Now, in that function, I calculated the first derivative, and this function returns the first derivative. After defining this function, on the next line, I wrote the rest of the script. Then again, we're checking if the active data is loaded. On the next line, we are assigning a variable called the result to the result of calling compute seismic derivative. But what's important is how we are calling this function. We're running it through my built-in mechanism, thread runner. So we have self.threadrunner.run task. Then we pass the function and all the arguments the function needs to run. Here we have one argument. You might run functions that need tens or hundreds of arguments. Totally fine, no problem. You just have to pass them right here. After you do this, you get your result. You check the result, you make sure the result is not empty, because sometimes you write a function that just doesn't go through, it throws an exception, and you end up with the result variable being empty. And then if you don't write this condition to check if the result is empty or not, it will be assigned to the active data, and it tries to add it to the data tree, and it will probably cause problems. So always check if the result is empty or not, and then assign it to the active data, handle the metadata, and then call the add tensor function to add the data to the data tree. But what if the function you're running takes a really long time? Seismic data can come in all shapes and sizes. Sometimes you just want to test a specific function on a seismic image, but you have no idea how long it's going to take. You run it and suddenly it's been running for hours. So you've had enough, you want to stop it, but what are your options at that point? You basically have to kill the whole application, which is horrible. That's not best practice at all. Force killing task is never a good idea. The other option is to unplug your computer, which is obviously ridiculous, so none of that works. Instead, we need proper mechanisms that keep the app responsive, something that doesn't force you to kill the entire thing or yank the power cord just to stop one runaway function. We need to be able to stop tasks safely. The problem with threading is that you can't actually kill a function running on a thread. Threads share the same memory space. They're not truly separate tasks you can just terminate. So if that function gets stuck, you're stuck too. That's not going to help us at all. So what do we do instead? This brings us to the third example. You can run the function using Python's multiprocessing module. With multiprocessing, that function runs in a totally separate process with its own isolated memory space. So if it starts dragging on forever, you can just kill that process, no need to kill the entire app or unplug your computer. Setting up Python's multiprocessing manually can be a lot of work, and that's exactly where SeismicFlow's task runner class comes in. To use it, you just put your main logic, maybe a function or a class, in a py or a pyd file. Then in your plugin script, you import that file, grab the function you want to run, and call the run task method of the task runner class. You pass in the function and all its arguments, and that's it. We'll get deeper into PYD files and Cython in the next video. Now let's take a look at the third example, the derivative task runner script I have here for you guys. So here, all we did was to take the function we used in the derivative thread runner example and move it into its own separate py file. That py file is now our logic module. Super simple. We just gave it a name, der.py. Der is short for derivative, and now we can import that module and run the same function with the task runner instead. Again, I'm importing numpy as mp. Always remember, when you write your own modules, you have to do your imports again because the memory space is completely separate, so that means the namespace is separate too. You have to re-import anything you need inside that module. So you write your imports in your py file, you write your function or class in there, and that's it. That file is your logic module. You can put this file anywhere you want, doesn't matter. Then you open up your plugin script. Here it's derivative task runner.py, for example. And in there, you add the directory of your module to the system path so Python knows where to find it. For example, my module is in the F drive py 3.12/plugins. So I add that to the path so it's accessible. Next, you import your module. So I import the derivative module, and then I assign compute seismic derivative to der.compute seismic derivative. That's how you access a function inside a module. You just go module.function. So here it's der.compute seismic derivative. Once you've got that, you check if your active data actually exists. You can also check if it's seismic data by checking if it's an instance of NP, like if it's a NumPy tensor. That's just good practice. Then you run the function using the task runner and assign the result to a variable like result. And here's the important part. Always check if the result is empty or not. This check really matters because when you're using the task runner, you actually have the option to stop the task midway. If you stop it, the result will be none. And if the result is none, you don't want to assign it to the active data, you aborted the operation, so there's nothing to save or attachment to data to or add to data tree. So that check is important, especially when you're running things through the task runner. Other than that, it works exactly like the thread runner in terms of how you call it. You pass the function as the first argument, then pass whatever argument your compute seismic derivative needs. In this case, it just needs the tensor data, so you pass in self.tensor data. That's the active dataset you're running the first derivative on. And that's pretty much it for using the task runner. Now let's talk about another way you can run functions. So far, we've covered threading and the multiprocessing execution pool. And now, the third option is using subprocesses. With subprocesses, you can launch a brand new Python process, but the big difference here is that you can launch it using a completely different Python interpreter. Why would you want to do that? Well, sometimes you need to run something that your main application's Python version just doesn't support. Like the main app might be running on Python 3.12, but maybe you have a library or an algorithm that only works on an older or newer version. That's exactly where subprocesses come in. So when you use subprocesses, you get all the same benefits you get from the task runner, which is the multiprocessing pool. You can kill a task at any point because it's running in its own separate process, totally isolated, but the big plus is you can pick which Python interpreter you want to run it with. Now here's how it actually works in practice. For the subprocesses task runner, you still have your actual function defined in your der.py file. That's the real mathematical function. But in your plugin script, you also need to make sure that the same function name is defined, just so the variable exists when you call the task runner. To do that, I just define it again as a simple placeholder function, as you can see here. This is needed because in this setup, you're not importing the module directly like you do with the multiprocessing version. Instead, you tell the task runner where the file is and which function of it to run. So this extra definition just stops Python from complaining that the variable isn't defined when you run the task. When you call run task, the pattern is the same. You call taskrunner.runTask and you set subprocesses to true. That tells it to launch a separate Python interpreter. You also set the folder name to plugins, the file name to der.py, and the module name to der. After that, same as before, check your results, make sure it's valid, assign it to your active data, handle your metadata, and add it to the data tree. And that's it. That's how you run your algorithms in a subprocess when you need a different Python version. So this brings us to the end of this tutorial on how to write plugins. I also have two quick examples to show you how to write GUI only plugins that don't do any math, just handle the interface. First, take a look at example matplotlib tabplot.py. This simple example shows you just how much control you really have over the GUI. When I say you get full control, I really mean it. Total control over Python, total control over the interface, everything you see in the app. In this example, I'm using one of the tabs in the application to show you how it works. I pick a tab using self.tabWidget.widget. That's how you access the tab widget. So if you want the third tab, you do self.tabWidget.widget too. Since it's 0 based, 0 is the first, 1 is the second, 2 is the third. Inside that tab, I create a simple matplotlib figure with 3 functions: sine, cosine, and sine times cosine. I define the signal, calculate the functions, and set up the axis labels. Then I create a figure canvas. That's the backend that lets matplotlib render inside the GUI. So basically, I replace whatever default renderer is in that tab with my own plot. To do that, I get the current tab's layout and find the existing child widget, the renderer that's already there. If it exists, I remove it cleanly with the delete later method. Then I create a new QV box layout, add it to the tab, and drop the figure canvas into it. Now the matplotlib plot shows up right inside that tab. So that's the first example, dropping a custom matplotlib plot into the application. The second example shows how to use the built-in 2D image renderer that SeismicFlow already has. Here I grab the last tab by using widget count -1, then I find its child, which is the built-in renderer for 2D images. I clear it and do the same thing. Define the signal, calculate sine, cosine, and sine times cosine, and plot them in blue, red, and green. I set the labels, add the legend, show the grid, and done. Next, I'll run each of these scripts and show you exactly what the results look like. And that's it. That's how you handle pure GUI plugins. Alright, so I have the SeismicFlow application open and ready to go. And I've also loaded the F3 seismic image. And I've plotted it just for you guys to see what it looks like in the 2D mechanism we have on the first tab. How do we add these plugins to the application so we could run them? That's the question. All you need to do is to find where you have your application, find the SeismicFlow folder, then go inside the internal folder and then try to look for the plugins folder. There's a plugins folder there. Make sure you are using the latest version of the application, 1.2.0. After that, all you need to do is to add your plugins in there. So we're gonna add all our plugin scripts right there in that plugins folder inside the internal folder of the application. Let's do it. We can do it one by one. Right now, if you go to the tools menu at the very bottom, there's no plugin. But when you add these plugin scripts to that folder, the list becomes populated and then the option will show. So we're just gonna copy our plugins and paste them inside the plugins folder of the application. So after we've done that, you guys can see the last option on the tools menu, plugins. You go inside that and you can see all these plugins that we talked about, right? Now let's apply them one after the other so you could see how these work. First things first, I'm gonna start with derivative. The derivative script was the one that runs the algorithm on the main thread. As you guys can see, it freezes the GUI. So best practice dictates that we never use the first option, which is just running everything on the main thread. Use the mechanisms I have in place for you guys. Please, let's be responsible. From now on, each and every one of us are developers, guys. You're all SeismicFlow developers, so let's be responsible. I'm gonna show you the result. As you guys can see, this is a perfect example of applying the first derivative seismic attribute. It can show us the thin layers. One of the reasons we calculate first derivative on seismic data is to find the thin layers. Now, this was the first way of doing this. So I'm gonna go with derivative thread runner. Let's see how the thread runner works. When you run it with thread runner, what happens is that you get this busy indicator right next to the RAM indicator on the bottom right of the application. And let's see what happens when we use task runner. So when we use task runner, you get a stop button as well. So there we have it. The result is exactly the same. And last but not least, we're gonna go with sub runner. For example, these are just arbitrary names. So sub runner, just to show you that it works. Then again, the same thing happened. As you guys can see, the result is also the same. So that's about it, guys. And also let's run those two plugins that played with the application itself. So I'm gonna have to open a couple of tabs here, but all of these tabs are empty, as you guys can see, right? Except for the first one. Now let's see what happens when we run the graph tab plot or example matplotlib tab plot. Let's see what happens. I'm gonna start with matplotlib. There you have it. As you guys can see, it swapped my mechanism for the matplotlib. And last but not least, I'm gonna try out the graph tab plot. Let's see what happens there. As you guys can see, it used my built-in mechanism for rendering 2D images, and it rendered the cosine and sine and multiplication of them, as you guys can see here. So these are obviously just some creative examples of how you can write plugins for the application and how much control you have over the application. Obviously now you guys have complete control over the application. You can write whatever plugins you want, whether mathematical, algorithms or GUI functions. You can create new dialogues. So this was our beginner's guide to writing plugins for SeismicFlow. In the next episode, we'll cover the advanced guide on how to create plugins for SeismicFlow. We'll talk about how to build highly optimized C++ or Python libraries, how to create PyD modules for Python so you can use them in your plugins, and how you can benefit from the significant boost you get from Python or C++. So the sky's the limit, guys. Let your imagination run wild. I'm looking forward to your plugins. If you have any question or feedback, feel free to shoot me an email. I'm always here for you. Let's create plugins together. And by the way, if enough people write plugins, we'll have our own plugin store where you can download plugins right inside the application. We have a lot of exciting things coming, and I'm really looking forward to your thoughts and your feedback. Thanks for watching, guys. I hope you enjoyed the video. Please make sure to hit the like button, comment, and subscribe. And as always, I'll catch you in the next one.